And what I can do after training is save the model. I do not have to do that. I can just work with that model I trained, but then I lose it, and training time can be significant. I needed for the 135 epochs on the model defined. It took me about 2 hours, which is not a lot still, but it's 2 hours GPU time, and that's reasonable. But it's still a very simple network. And then I want to save it, and I can easily do that by calling torch.save and inputting something which is called model state dict, which just describes all of the different weights I've just learned and the shape of or the architecture of the model, and I give it a name, which is model checkpoint. What I can then do is, before I go to the inference example, or what is missing, what's something I can add if I wanted to add to it. Again, this is still pretty simple, like the adjustment of the learning rate, which the Mueller paper proposes is not covered. That's something I could implement and add. There's an optimizer in PyTorch that wraps the optimizer that I can actually feed with a specific learning rate schedule. I think it's called LR scheduler or something, and that's something you could implement to do that learning rate schedule. And obviously, not right now, even during training process, I may want to validate some of the results on a distinct validation data set, which right now I was not doing. Inference. So how does that work now? I have the model stored, and I'm assuming it's a good model. I may want to check it on a test data set or validation data set during training, but let's assume it's a good model, and it actually works reasonably well, right? It's not just an assumption. I can instantiate the model again. That looks very similar to TensorFlow because I have to instantiate the network architecture on one side, and then I have to load it with the pre-trained weights on the other side. Something I actually have to do if I want to do the inference on CPU is I now have to tell them it's actually running on CPU. Something done here. I think it saves. I don't actually know why that is. I think because I saved it after I've been working on GPU, it saves that GPU device allocation as part of the model. It's something we do not want for the inference potentially, so we just map it to the CPU, else it would try to run on GPU. I get new data, and this is just randomly from the train data. So there is a chance, obviously, it overfits on training data, the model. But for tutorial purposes, that's fine. So that's the ground truth. I have two persons here. A smaller one on the left and a larger one in the middle of the image. There's a definite difference in sizes of those two persons. And then I can do one thing. I can predict using the model and see if I get to something that's similar to the ground truth. And that's what I'm doing now. There is some magic again involved in Torch tensor magic in reformatting some of the data I get so it actually gets into the shape I can work with. Remember, I guess the most important one is all of the different cells will have a prediction, but I want to filter, and I also want to only use the prediction that exceeds a certain threshold, because else I get 49 different predictions for the entire image, which is how YOLO works, right? But you want to take a confidence threshold and say everything more than 0.5 confidence in that prediction is what I actually want to use for inference, and that's a filtering step you have to take. Yeah. Correct. Correct. Right. So the grid responsible is the one in the middle of the box, right in the middle of that box. And so if you take the center of that box, which would be here, that's the grid responsible for that prediction of that specific. Right. Well, not the bounding boxes can exceed the grid dimensions, if that's what you're asking for. Every grid you can does a prediction, and you get a class bit per grid, but the bounding box can exceed the grid. It's just the max. The only thing YOLO does is saying every grid can have, to make it simple, every grid can have one prediction. So I only have a maximum of 49 predictions, which is bad for smaller objects. Correct. Correct. Correct, correct. Correct, correct. Correct, correct. Yeah. I think it becomes more clear if I show you what actually is happening, because I plotted some of the tensors. So this is the ground truth. It doesn't. This is, I can highlight it in blue. This is the ground truth, and you see, those are the 25 values I was discussing earlier. I'm ignoring what grid they belong to for this specific purpose, but let's assume this is one grid and this is the other grid, and each grid will have, in the ground truth, will have a value for the x, will have a value for the y, will have a value for the w, will have a value for the h, and will have a confidence. And in the ground truth, the confidence is 1 because I know there's an object, which is my 1 here. And then if I go through the last 20 values, this is my my one-hot encoded class definition, and I see there's a 1 for this value, which would be person. And that's essentially how the ground truth data looks like for each of the different cells, and that's what I'm trying to predict. So if I do the prediction, I will end up with a tensor that looks exactly like that for 49 times for each of the cells in the grid. Does that make sense? And those are the values I actually want to predict. And you see the fifth value is the confidence. I will end up with in my prediction, I will end up with a tensor like that for each of the cells, but I filter and I say I only want to take care of those that have a confidence higher than a threshold, which I set to 0.5 here. So it's or something like that, right? So because the confidence, which is the fifth value, that's how it's encoded, is 0.69, I'm keeping this prediction. And for the nighttime one, the confidence is even 0.97. So I'm pretty confident that there's something, that there's a bounding box detected, and that's why I'm keeping it here as well. Yeah, sure. 7 times 7 times 25. For every grid, you have 25, correct? Yeah. No, I think these should be 25. Oh no, the 7 times 7 because I'm only showing those with actual objects in. Yeah. Yes, correct. 49. Correct. So overall, it's a tensor again. It's just different dimensions, right? It's a multi-dimensional. Well, tensors are pretty different, multi-dimensional, but it's 7 times 7, and then you have the 25 value. So it's in itself a tensor, but I'm reducing the shape and the size of the tensor to those cells I'm actually interested in for this case. Correct. It's just, yeah, and I think the issue the bounding box doesn't have to be within that cell. It can the only thing that needs to be there is that the center of the bounding box is in the cell, and that's how bounding boxes are assigned to a specific cell. The size of the bounding box can and will exceed the cell. It's a prediction, right? It's a value you predict. You have the ground truth. You know how the bounding box actually looks like. Or it's a regression problem then, right? And then you want to predict, then each of the different cells predicts a value for the bounding box. So if you look into this one here, what this cell is predicting, for example, this is my x and my y, and this is relative to the cell, right? This is the center here. Those two values describe the center relative to the cell, and this is my width and my height of the value. Correct. That's correct. But I have maximum of 1 bounding box per cell, I'm predicting. Confidence is also something I learn. There's the confidence. Right, and the confidence is also something the model learns, right? In the ground truth, I said confidence 1 if I know is somebody, and I said 0 if I know there's nobody, and the model will also learn the confidence values. And that's what I use to filter, yeah. Yeah. So it's a different.
The pictures could be different.
Yeah, it takes a random picture from. There are many pictures.
If you compute it, it will be different. The thing in the box's number is different. So I assume it's different version than what we had there.
Well, it's just it's the code should be the same, but if you execute it, you take a random image, you potentially predict a random image, right? It's not fixed on that specific image. No, it's the same version. If it's the same version as far as the code is concerned, but if you execute it, you can. There are some randomness involved. No, that can't be because we just committed it in the morning. But there's a randomness involved, right? We can look into that, and I can explain you where that comes from maybe after, if that works. Sorry, I didn't get. Yeah, there's a randomness involved. Yeah, randomly. So correct. Okay. Great. Yeah. Correct.
But there is a reason in the theory why we want to make the back size big.
Agree.
Otherwise, it will be underdetermined, and then we can get
correct.
non-correct value.
Correct.
So, what is your suggestion to us? Should we try to use the batch size as much as we can afford with our computing power, or?
For this specific case, if you can afford 64, you should go with 64 because they've been proven for that to be the best. But if you can't get everything into GPU memory, you obviously have to reduce it somewhere, right?
Sure, of course, yeah. And then let's say we start with a small batch size. Actually, the training will show us if it doesn't work, right?
Yeah, if the loss is not going down, correct. What will happen is the loss is potentially not going down, and that's something you see during training.
So it means that, your website isn't good.
It doesn't have to, but it could be one thing. If you see that during training the loss is not going down, you have something is wrong. That actually happened to me doing this first, and then I realized because the batch size was reduced, I had to reduce the learning rate as well. The loss was yeah. There are many parameters to that. Sorry?
Do you have any sample output errors when the data doesn't fit?
Well, the CUDA will tell you that it's out of memory. I don't have it, but you will get a message that the GPU is out of memory. Yeah. Oh, well, yeah. I think, well, there are two things. The confidence in the bounding box is not necessarily related to the class, right? The confidence is in there being a bounding box for any class. Class imbalance, I think the data sets are pretty balanced. I didn't check, but I think they're pretty balanced. You get a lot of data. That's correct, yes. That's correct, and that's why after filtering with confidence, I end up with only 2, which happens to be the correct choice, right? Because there are 2 objects detected. But that's correct, yeah. So did you have to what steps did you have to take to go for that? There's no step because that's how the data looks like. You're just predicting how your ground truth looks like, right? And the ground truth looks exactly like that. There are not a lot of objects or not a lot of bounding boxes responsible for prediction on the outside of the image, and that's also then how the network is learning it, and the network will behave. You had another, yeah. Yeah, it actually, if you have a GPU available and the drivers are correctly installed, it's coded to run on GPU to device. If device is a string called CUDA, it will put it on the CUDA GPU. So that's how you name it. There's CPU and there's CUDA, which is just strings determining the devices you run on. It'll be more challenging if you want to run on more than one GPU, but one GPU is pretty straightforward. You can move them from GPU back to CPU or back to memory if you wanted to, but if you need them for one computation, they have to be on the same sort of device. That's correct. And no, you can also calculate it on a GPU. I just wanted to show that that's technically possible. But then again, in the loss, maybe there are not a lot of backprop operations in the loss, so it's not really that relevant whether it sits on the GPU or not. And in general, the GPU memory is as long as it's what more becomes a bottleneck than the other memory, and most of the times, right? If you code efficiently. Okay, thank you.
Yeah, we're definitely running a little behind, but this was very interesting and very good. Thank you, David. Yeah, lots of examples, and as we mentioned that there's two approaches. This is of course the single shot based, the two shot based approach that we talked about, and that's kind of what we'll go into the next section. Is that was supposed to be the break? No, I said no. Sorry. If we do that, then we will not have any time at all. Let me just. Okay, good. So we talked about detection, object detection. If you want to get even the next level is segmentation, right? So there is scene segmentation, which is segmenting an entire scene and all the different aspects of it, so background and objects in it and things like that. You saw that little video of the road data set. And then there's object segmentation or instance segmentation, which is just finding the specific object within an image and drawing a polygon around it, right? So there's a surfer and the surfboard, and those are two objects that we have. So the annotation, as we showed the annotation for bounding boxes, which was now looking back, it's just so simple because look at the annotation for segmentation. It's a lot of points and a lot of detail. So the biggest challenge right now with segmentation is the lack of this type of data sets. It's very costly and very expensive to segment images and object instances. And this is a chart from Crowdflower. They did a report on just their experience working with images and labeling. And look at the the semantic segmentation is the most expensive. Even polygons are more expensive, and then bounding boxes are the least expensive. Everything from time commitment and all of those things definitely send you in the direction that segmentation is very. Getting the data for segmentation is the big challenge, right? So to that end, there are two major approaches to segmentation. One is and this early on, encoder decoder was the most popular, but the newer approaches are region-based. And so encoder decoder is simply, going back to the convolutional neural networks discussion that we had earlier, you just extract to a certain point the low-level features, and once you have gotten to a point, you can then actually start doing deconvolution or upsampling of the same image, and you are now getting boundaries around the objects. Instead of actually doing object detection or classification, you are just getting boundaries. So there are several architectures. The fully convolutional networks is one of them, SegNet, UNet, and there are many other approaches to this. the region-based segmentation is something that we saw earlier in faster RCNN, and then what they did is that they took to the next step, which is adding a third predictor for that. So mask RCNN, PSPNet, and learn to segment all things. These are all the types of segmentation models that are moving towards using a combination of bounding boxes to build masks on top for object segmentation. One thing I'll note here is that I'm mixing a couple of things, right? So there is a clear distinction in scene segmentation, which is something like this, right? Where you are pretty much trying to draw boundaries around all the different things within a scene or photo, so to speak, versus object, which is what you saw with that surfer and the surfboard, right? That's just the instance of the object you're trying to draw segment around, right? You're trying to segment. So so there is a new challenge out there for called just brains freeze. I think it's called panoramic segmentation, which is both the scene and the instances within it. And this is like very critical for like self-driving type things, medical, and some of the places where accuracy is very important, but to a level where it has to be very accurate. Right? Drawing a bounding box is not good enough. You need to be very precise and accurate where exactly is the boundary of this object versus the next object, right? Or it could mean like the car hitting something versus being able to get by, right? Because you can't just we don't, our world is not boxes. It's all sorts of different shapes. So going back to the encoder-decoder based model, the full convolutional neural networks was one of the approaches, and there's a PyTorch implementation. The code is a little kind of complicated, so not enough time for us to walk through the code, but if you're interested, there is a PyTorch-based approach. And as I said, the idea here is that you take an input image, and then you start doing convolution layers on it, and then also the dimensional reduction pooling steps to get to a point, and then you upsample that image so that you are now drawing boundaries around the different things in the image. So that's a very, very kind of early on. That was an approach that was getting good results, but the team that worked on faster RCNN, they said, well, we are going to go in a different direction, and we are going to build a third predictor on our faster RCNN model. So David showed a picture of that where I'm on my presentation mode, where you had the classifier, which was telling you the label, and then you had the regressor, which was telling you the bounding box in a faster RCNN, which is the improvement they made in 2016. And with the mask RCNN, what they did is that they added one more predictor to it, which was going to be for every pixel a binary, 0 or 1, if the prediction was there or not, right? So because this is for objects, not for scenes. So you're looking for specific objects and their segments, right? So the big change was that in the bounding boxes, their loss was based on ROI of region of interest pooling, right? Versus in mask RCNN, the loss is based on ROI line. And so let me just explain that a little bit better. So the difference, and this is essentially, this picture right here is showing you how they added one more prediction branch, which was for the mask. So you had the regressor for the bounding box, you had the classifier for the label of the object, and then for the mask, they added one more, which is based on deconvolutions, and the final loss was based on the alignment of the ROI. So if you think about ROI pooling, it's simply you're looking for the maximum value. Like if you're looking max pooling of the region of interest, right? So you're saying just give me the highest values, which will draw a border around an object. Instead of that, they said we are going to use something called alignment, which is based on interpolation, right? So it's not picking the highest value; it's picking the closest one that makes sense. So there's in PyTorch there is for upsampling, right? So instead of simply upsampling based on the highest pool value, you're now actually doing it based on some alignment closest to where the boundary should be. There is in PyTorch there is essentially a function to do this called interpolate, which just allows you to upsample based on alignment. So that was that has been a big development for segmentation, and I have a link to this a good implementation in PyTorch. I will put this on, or I'll just paste it in the Slack. I didn't get a chance to do that. Lastly, what I wanted to cover from the segmentation perspective is that the overall topic is very hard, and so the same authors who did the masked RCNN this year-ish, I think maybe earlier this year or late last year, they came up with a new paper called "Learning to Segment Everything," and that's essentially they want to combine the segmenting objects and the scenes. And the biggest thing they did is that the lack of data sets, right? They fully acknowledge that there's not enough classes. So we said, even like Coco dataset has how many classes for the dataset, versus when you look at the segmentation classes, it's like very few, like 70 or 80 compared to like thousands, hundreds plus for the for bounding boxes, right? So the approach in the learn to segment everything was using the masked RCNN type network, but at the same time you're using the bounding box weights as something doing some transfer learning on that for your segment prediction. So you are maybe trying to get a shortcut to where you need to go to segment the object instead of trying to figure out in the whole image where the object should be. So you're just saying, oh, this is where the bounding box is. Okay, I now have minimized my problem to that area. What was the other thing I wanted to mention in here? So some of the key innovations were the weight transfer function, and then so the state with this is that there is no PyTorch model that is very good for this right now, because this is still fairly new. This was implemented. I mean, this is the team that is at Facebook and Berkeley AI Research. What they've done is that they implemented this in Detectron, which is in Cafe 2. It's kind of like Facebook's big contribution for object detection. Detectron is the Facebook's contribution for object detection and segmentation, but it's written in Cafe 2, which is also one of the frameworks that is very popular at Facebook. But considering that Cafe 2 is merging into PyTorch, sooner or later we are going to. There are some people who have done Detectron implementation in PyTorch, but it's still not as robust probably as something that Facebook is going to come out with, that will be a Detectron version of in PyTorch, which will have this model ready for you to try. So segmentation is still a very developing area, a lot of challenges, and the authors of this paper, you can check it out, are saying that this is like a baby step into the direction, semi-supervised approach towards segmentation, because there's just not enough annotation data. Anybody who's tried segmentation for objects or scenes, it's a difficult area, costly, difficult and costly. We have about 10 minutes, so I just want to talk about a few other odds and ends. So one of the things that we for taking PyTorch models into production, and this may become kind of obsolete in probably another month or two. Is currently you can take PyTorch models and convert them into using Onyx into other frameworks. So of course, Cafe 2 is readily available. I'm not sure what's going to happen with ability to take PyTorch models into Microsoft Cognitive Toolkit or MXNet, Apache MXNet. But it's a very simple process right now in PyTorch where you bring in the Onyx module and you say you want to export a model, and simply just say here's the model file here's a model, here's some dummy input that I'm going to have, and save it under this model file, which is a protobuf file, and then it goes ahead and creates a readable model that looks like this, but it's compiled that you can take it into Onyx. So here's the Onyx code where you bring in the AlexNet proto. So for example, David's YOLO model, we could export it as a protobuf file and bring it into Onyx, and then and then into Cafe 2. And Cafe 2 can allow you to deploy it to iOS or Android or many other ways. So there's lots of inference mechanisms in Cafe 2. So that's kind of the way right now. As you can imagine, it's not very straightforward. Hopefully, this is where the biggest changes we'll see in PyTorch, where you could pretty much take a PyTorch model and then compile it down to iOS or Android or whatever other things. So stay tuned for that. That will be something that I'm looking forward to in the coming months. Over the break, I had a couple of discussions around just some of the issues in the space. So one thing that did you mention data augmentation? I don't know, right? PyTorch has several methods for data augmentation. So you can take your data and apply a lot of different all these different transforms to augment the data so that you can deal with all sorts of abnormalities when you go out in the wild, right? So, and then to that end, there is a good paper around data augmentation and why it works so well. And so in that paper, they have gone and said that by applying all these different data augmentation techniques, they've improved the state of the art of certain models and things like that. So, this is so if you're dealing with situations where you may have like glare or some kind of all sorts of abnormalities when you are from your training data set to your actual production data set, it would be very good idea to augment your data for training purposes, so you can get a better trained model. One of the other things that David and I were discussing yesterday that we haven't really come across anything good for parameter optimization in PyTorch. I'm sure there are people who are doing that. That would be really nice. Of course, there's a huge challenge once you start getting bigger and bigger models. What are the best parameters without having to try it like 15,000 times and 2 hours at a time? We don't have enough time, right? So it would be that's another thing it's a challenge that would be good to get some work around. I see, Google and others have AutoML and all these things that are coming out. Those are kind of in that direction. Models are getting bigger. That's of course one of the issues. So you need bigger and bigger hardware to kind of be able to. So it's like, yeah, it's great. We can take transfer learning, awesome, but these models are getting bigger. So it's not as easy to just say, yeah, I'll just take the most recent model and then start using that for my kind of initializing my training. This is an old paper by now because I think people have beat this, but it cost $1 million, close to $1 million to get the ImageNet training time to 24 minutes, and such is the case right nowadays. It's using GPUs and other methods are absolutely critical if you want to do some real production level training and then inference. I was discussing with somebody that yeah, inference is still a big thing. Being able to do mobile level inference at high speeds is still something that's not solved. Some of the things that we didn't cover that are definitely computer vision topics. GANs, generative adversarial networks, are huge. There is a PyTorch. In PyTorch, there is an example of a generative adversarial network. So if anybody's interested, they can check that out. One thing that has been recently, and I'll say within the last year and a half, discussed a lot in computer vision is capsule networks, and that's something else that's coming up in the horizon. So hoping to see some. Let's see if some PyTorch implementations of that and how we deal with that. So that. That wraps it up with 5 minutes for any question and answer. I know there were some curiosities. Yeah.
May I ask about image size? So regular images can have different aspect ratios, right? But these training networks are usually with size 1. So if a solution might be resize my new test image, aspect ratio 1, right? But then my face will get this weird shape, which is not training network. So what are common solutions for regular images which don't have aspect ratio 1? Do you have an idea or
I'll ask David for his opinion as well. My opinion is that at the end of the day, you want to learn low-level features. So like training, well, number one, it would be impractical to train it on like super high resolution images. But my thing is that it may not really matter.
No, I'm not going to retrain. I'm going to use one of the models.
Existing models, yeah.
Yes, but for the inference, my image size is not square.
Yeah.
So
Oh, okay.
Well, the easy approach is you reshape it and you predict, and then you shape it. We put the shape back to how it's supposed to be looked like.
If I reshape it, then I will have this weird, not real, bad.
But that's just for the model, right? The model will.
No, I'm not going to retrain the model. I'm using an existing model, right? And I would like to test my images, which are not square aspect ratio.
Right, but you can still even for inference you can still reshape it to the input format the model would accept, do the prediction, and then just shape it back to what you need, what was the original aspect ratio and original size, together with the predictions you would have to shape that.
This is the type of thing that really addresses this, right? Is that if those models were trained with data augmentation for skewing and stretching and compressing and all sorts of different transformations that can distort the images and still do the correct prediction, then you should not have a problem if you change the aspect ratio.
So your suggestion is open some data with your skewed aspect ratio to the training model, and then see if your new aspect ratio is working.
Yeah, my bet right now is that it will work without you having to do anything.
Like if my face is elongated.
Because I'm thinking that the people who have done some of these more advanced models, they've done a lot of data augmentation to get good results. But if not, then you can always retrain the last few layers by doing some of the data augmentation techniques on your models. Yeah. Any other questions? Yes.
Is there a RetinaNet example for PyTorch that you recommend?
Did you come across anything?
I think I had a look and I think I didn't find anything I would recommend. There's not been a lot. There were some implementations, but nothing that where I looked at it and say, hey, this is it. This is something I have to look into in more detail.
Do you know if the whatever state of the art is in TensorFlow?
Not 14.
Yeah, it's well, sometimes researchers don't publish the code. It's becoming, of course, more and more are, but some don't, which is difficult. It all depends on where it's coming from. Typically, Google, Facebook, they tend to put their code out there. Yes.
What's the equivalent of TensorMore?
There
Yes,
is this
yes.
wisdom.
TensorBoard, or what was the question?
Yeah.
Yeah, you can use TensorBoard as well for
Oh, you can?
PyTorch. Yeah. You just have to store during training your data in the right format, and TensorBoard can read it. But I've seen people doing that. Yes.
The protobuf, right? Or
The logs have to be stored in the right format.
there is
yes.
what I came across was this thing.
I think even part of the official tutorials have a TensorBoard. Or I saw
Oh,
it
is that right?
somewhere
I
in
didn't know
the
that.
Yeah.
Maybe this is just for visualizing data
Yeah.
models.
No, but you can use TensorBoard. Yeah.
Okay.
Nothing stops you from using TensorBoard.
Yeah.
About the batch normalization, I think it's very crucial, the normalization part, but in code that you went through, there
Yeah.
was no batch normalization.
You mean as a layer in the network?
Yes.
I just went with the YOLO V1 network basically. So that's what they suggest in the paper, right? I didn't want to add or.
I mean, a normalization function. So there is no normalization. So
There was a regularization in.
You mean well as part of the network?
yes, as part of the network, normalization constrains the size of the vector. So and I think
There are some.
you mentioned batch normalization in the beginning.
Yeah, I'm just checking the
I
model.
think for those who want to leave, that's fine. But we will be around for questions, so just